Your plane reaches the gate, the seatbelt sign dings, the doors open, and within minutes the cabin empties out. To anyone watching from the terminal window, the aircraft looks finished with its job, ready to wait for the next flight. On a short-haul schedule, that plane has roughly 45 minutes to become a completely different flight. And under an hour, it needs new passengers, new luggage, fresh catering, clean water, a verified load, and a new fuel supply. These jobs cannot happen one after another. There isn't enough time. All these distinct tasks require the same aircraft, the same doors, and the same narrow patch of concrete at the exact same moment. During this window, the stationary aircraft functions as a temporary factory. It exists to produce exactly one thing: a machine that is safe, complete, balanced, and ready to leave exactly when the network expects it. If one critical job in that factory finishes late, the aircraft misses its departure sequence. That delay follows the plane to the next city, disrupting connecting passengers and consuming the time buffer of the next turnaround. The race to turn the plane around starts before the airplane arrives. While the inbound flight is still descending, the next departure already exists inside the airport's digital systems. Ground teams know which aircraft is coming, the gate is assigned, and catering requirements are prepped. This preparation requires exact timing. Ground teams must reach the stand in a specific sequence. A baggage team waiting at the wrong gate is a team unavailable somewhere else, and a fuel vehicle positioned badly before the plane stops can block every other service. When the aircraft finally turns toward the stand, its final position must be precise. It has to stop exactly where the passenger bridge can reach the door, where fueling equipment can hook up, and where baggage loaders can access the holds without striking the aircraft skin. Once the plane stops, the mechanical sequence begins. Wheel chocks secure the gear, and the engines shut down. Ground power is connected to the fuselage so essential aircraft systems can continue operating without relying on the plane's onboard auxiliary power unit. Only then does the factory fully assemble. The exterior of an aircraft is covered in delicate sensors, engines, and control surfaces that create strict safety zones. Ground crews generate speed not by rushing these areas, but by designing every single movement around them. This precise choreography prevents the intense demand for speed from resulting in a collision that damages the aircraft's exterior. Inside the cabin, the arriving flight is being erased. As passengers leave, cabin crew check for belongings and damage while cleaning teams remove waste and reset the seating areas. At the same time, caterers remove used carts and load fresh ones. These jobs compete for the narrowest workspace in the entire operation, the center aisle. A single cart stopped in the wrong position prevents any other team from passing. Resetting a cabin is a flow problem. The fastest cleaner cannot finish the job if the sequence of arriving passengers, caterers, and crew prevents them from moving through the aircraft. Below the floorboards, another turnaround is running in the opposite direction. Inbound bags are separated between local claim and connecting flights, while outbound luggage arrives from the sorting system to enter the correct hold. This chart shows how an aircraft's total weight and its distribution are affected by passenger numbers, baggage, and fuel. Load control staff use this information to dictate exact baggage placement, ensuring the final load matches the flight plan. If a passenger fails to board, staff may have to locate and remove their specific suitcase. One missing traveler can send a worker back into a fully loaded hold while the departure clock continues to run. The narrow cabin aisle and the dense baggage hold impose the same physical bottleneck. Moving a single cart or suitcase out of the proper sequence stalls every other task in the reset. Outside, fueling is undergoing its own exact calculations. The aircraft does not request a full tank by default. The fuel team delivers an amount calculated around the upcoming route, expected weather, and mandatory reserves. Other fluids move through the turnaround through separate systems. Potable water and lavatory waste removal use entirely different equipment and service points to prevent a sanitation failure inside the cabin. While the fluids are managed, pilots or maintenance crews perform exterior inspections. They are looking for leaks, tire wear, or surface damage. Discovering even a minor defect instantly creates a schedule risk, as the aircraft cannot depart until the issue is assessed through approved procedures. To manage these moving parts, the turnaround relies on a coordinator. This person does not personally load bags or clean the cabin. Their job is to monitor the dependencies between every active task. This logic tree shows how parallel tasks interact. A water truck running a few minutes late may still finish before the doors close, but if the final baggage cart hasn't reached the aircraft, that delay moves the departure. The coordinator must identify which of these late tasks is currently threatening pushback. By converting the turnaround into a series of shared digital milestones, the gate and the ramp avoid operating with different versions of reality. This digital awareness provides a safeguard, ensuring that the pressure of the clock never overrules the physical readiness of the machine. As departure approaches, the shape of the operation changes. Early on, many jobs run in parallel. In the final minutes, every physical action must tightly converge. Departure readiness is binary. An operation that is 99% complete still means the aircraft is functionally stationary. A single unresolved passenger count, one open cargo door, or one document that does not match the physical load is enough to halt all momentum. Once every critical condition is satisfying, pushback clearance is granted. A tow bar-less tractor lifts and controls the nose gear directly to move the plane backward, as engines are not normally used to reverse from the gate. Then the temporary factory disappears. The passenger bridge is parked, service vehicles clear the stand, and the gate begins preparing for whatever arrives next. The speed of this reset affects the entire schedule. A 5-minute delay at one gate enters a network of interconnected routes, crew limits, and air traffic slots. If the next turnaround is also tight, the system inherits the delay rather than absorbing it. A successful turnaround is the synchronization of dozens of independent systems. The aircraft departs on time because none of those systems were allowed to fail in isolation, preventing a localized bottleneck from spreading through the rest of the day's schedule.